Kirumbi Engineers Skills Academy. We are available at Dar es Salaam, Tanzania, East Africa. You may contact with us through phone number +255 737 72 1910 or +255 787 85 74 85. Email us kirumbiengineering@gmail.com. Website kirumbiengineeringacademy.ac.tz. Analysis of the section of the structure. The shear and the bond, the serviceability and the durability of the requirement. Now, design of the beam, a slab member, a column. Now, first one, as we said, we start with the properties of the concrete. Now, the properties of the reinforced concrete as follows. There's a so-called the composite concrete and steel. Now, the steel bar is embedded to the concrete to strengthen the concrete in tension area. Now, always we say the concrete is good in compression. So, general properties of a concrete, it is higher in compression strength, and if you add with the so-called steel or steel bars, which has the higher tensile strength, so the so-called what you got is general, as we say, the addition of the concrete, I mean the compressive strength, plus the tensile strength, which is from the bar, you got the so-called reinforced concrete. That's why we call the concrete which is reinforced. It means the concrete which is added with the bar steel or the steel bar. So the definition of reinforced concrete is the summation of the concrete including the bars. If it has no bars, it is called the mass concrete. So the general properties of concrete has highest compressive strength. Now, the general introduction. Now, the reinforced concrete combine the best features of the concrete, in which there is a concrete and there is a steel, so which are complementary as follows. Now, the properties. Now, here we have the concrete and here we have the steel bars. So what it is, the concrete, if you consider in terms of strength in tension, the concrete is poor, but the steel bar in terms of tension, it is good. But if we consider in terms of strength in compression, the concrete is good, but the steel bar sometimes it's good, but it is slender, bars will be buckle. So note that the steel bar is not much good in compression, but it is good in tension. So once it is slender, the bar will buckle automatically. Now, in terms of shears, the concrete it is fair, while in terms of shears, the steel bar it is good. In terms of durability, the concrete is good in durability, but the steel bar it collides. So if it is not protected, the steel bar it is coming to rusting. So in terms of fire resistance, Also, the concrete is good in fire resistance, but the steel bar, it is poor. So it is very suffering or rapidly loss, or it loses its strength once the temperature is very high. So that is uh, the general properties in both members, in terms of concrete, also in terms of steel. So the comparison of concrete and steel, in terms of tension, as we said, it is poor in concrete, but it is good in tensile. The steel bar is good in tensile. The vice versa, in terms of compression, the concrete is good in compression, while the steel sometimes it is back automatically. Now the shear, it is fair, the steel is good. In terms of durability, it is good, while here it collide once it is not produced. So in terms of reinforcement, the concrete is good it is good in fire resistance, while the steel, it is going to lose its strength for higher temperatures. So that's the general and this what is shown here, it is some of the member in terms of longitudinal and cross-section. So in terms of longitudinal, these are the bar and these are the steel up, and these are the general concrete in the member. So the bar, it is inside the concrete, that's what we call the reinforced concrete. In terms of sections, you see the sections and the bar links there, and the main bar, it is like that one. That's the cross section of the members. So general introduction, and in general introduction, the reinforced concrete is used to produce the structural element of the member or the buildings or of the structures. The such of the structural members, we say the beam, the slab, the column, the wall, the stair, and the foundation. And here is some of the members. This is the stair. This is the foundation sample, paddy foundation, and this is the sample of the stair. If you consider about the wall, it depends. Sometimes it might have like this one, and this is the color. The slab is like this one, and the beam is the one which carrying the slab. So the beam, it might be like this one underneath of the slab, or like this one underneath of the ribbed slab. So that are some of the members as in the structures. So to ensure the structure is safe and is suitable for occupation with the minimum cost, so stage 1, we need to have the so-called planning. In planning here, there is a client, there is a function of the planning, what the nature of the structure is usually, the environmental structure factors, economical factors, lab, site survey, the structural configurations. These are in the planning stage, all these are in the planning stage. While in stage 2, in the structural analysis, here we consider the design constraint, the action, the static of the equilibriums. Here is in terms of force, reaction, internal forces, the moment, the shear, etc. So the material properties, the strength, so the elasticity of the material, everything it is in this second stage here. So uh, once you consider on the second stage, these considerations should be taken into account, and this consideration is as described here. You pass through, you can see in the second stage which the consideration should take. So on the third stage, you consider the member design here is, once you consider the code of practice, so maybe you use BS code, or you use Euro code, or Indian code, Brazil code, etc., etc. And it depends on the nature, whether it is reinforcement or reinforced concrete or steel structure or bridge structure, whatever. So all these consideration is in stage number 3. And once you go to the stage number 4, in this stage is the construction stage. So here is the way you implement both the planning stage, the construction, the inspection, the supervision of the structure, and the monitoring and the quality control. Both of these are at stage number 4. Now, as we said, the relevant introductions on the planning stage, here you can have the drawing in terms of architectural drawing, which will give you the nature of your structure, the use, etc., etc. So all these function is here is in the planning stage. So the architectural drawings concern this as shown. So also there is a structure drawing. Here you check the analysis and design whether it passes or it fails. So both the key, the foundation, the floor, the roof, the detail, all are described in the structure drawing as once you complete to design. So the composite action. The composite action is the concrete, you say it is weak in tensile, about 10% of the compressive strength. Now, once the design assumption is as follows. We say that concrete does not resist the tensile strength. This is the first assumptions. The second assumptions, we say that the reinforced steel carry only the tensile force, in which it transfer the bond between the interface between the two materials. So once you want to design, the consideration or the assumptions is, as we said, that the steel is good in tensile while the concrete is good in compression. So once we consider the steel is good in tensile, we assume that all the tensile force is carried out, or it is resisted by the steel. It means the concrete does not resist anything. This is assumption, but in reality it is not like that one. So also the second assumption, we say that the reinforced concrete, it carries the tensile forces, which are transfer the bond between the interface of the two materials. The two materials means the steel bars and the concrete. So both of them are the two combined which make the so we call reinforced concrete. So before it is no stress, the member will it will be horizontal like this one. Here no load is applied. It means no any stress appears, as if it is you have your member and already there are no any load appeared above or on top of the member. But once you load it, it means the upper part, it is appear as a compression, and this is the part of the concrete. It means it appears as the compression, while the bottom part it appears as the tension. So by this way, we assume that it means our member, it is in compression above while it is in tension below. So this is after loading. Here is before loading. So by that way, we can say that the above, it take the compression, the one which take the compression, it is the concrete, while the bottom, it take the tensile. So the one which take the tensile is the steel bar. So means you have the compression and the tension. And that's why failures, the failure, concrete strength exceed, once the concrete strength, it is exceeded. Also the failure, it is once the steel strength is exceeded, or the bond fail. It means the bond between the concrete and the reinforcement, it is fail. So always the member will appear to fail. And these are the general rules, or the general explanation on how the concrete appear, or the concrete member appear once it is loaded or before loaded. As we said that before loading, it is no stress, and after loading, the top part, it is compression, while the bottom part, it is in tension. So this is the way how the assumption comes from, as we say that we assume that the concrete has no tensile force. It means the tensile force, it is all carried by the steel bar member. That's the assumptions. Now the composite action. If the bond is inadequate, the reinforced bar, it is slipping, there will be no composite action. Also, when the bar are normally ribbed, so there is an extra mechanical grip. So the assumptions, we say that the strain in the reinforcement, it is equal to the concrete. It means the grip is the nature of the reinforcement, whether it is plain or it is ribbed. So by the assumptions, means that if this is the section, of the member of the concrete, now if we consider this is a section of the member of the concrete, means the centroid or the neutral axis, say it is assumed like here, means that the above part, it appear as a compression, while the bottom part, it is appear as a tensile. Means that if you have the triangular, it means if we take this one as a section like this, and this is the center for the centroid of the member, it means your properties, it is appear like this one. It means the above part, it is appear in compression, while the bottom part, it is appear in tension. Means this portion, it has a force for the compression. It means the force for the concrete, while the bottom one, it is resisted by the tensile. As we assume that the concrete, we assume that has no any resistance to the tensile. So it means the bottom one, it is only resisted by the tensile bar, while the top one, we assume it is resisted by the concrete. It means the upper one is compression, while the bottom one, it is tension. And this is the general triangular block from the neutral axis, in which the above, it appear the strain for the concrete, while the bottom, it has a strain for the steel bars. So this is the neutral axis. So this is the way how we assume our assumption for the concrete. Now we look for the so-called stress-strain relationship. So the relationship between stress and strain is as follows. Now the load of the structure causes distortion of its member, with resulting the stress and the strain of the concrete and the steel or the reinforcement bar. So this one, the analysis of the stress and strain based on 8 equilibriums of the force. Now the horizontal force is equal to 0. Also the moment is equal to 0. And this is the basic engineering principle. So if we assume the compatibility of the strain, the linear relationship is developed as interpolation. So the linear relationship is as what we see here in the diagram, as we assume that this is the section of the concrete. As if we assume the section of the concrete from the neutral axis like this one, as we said, the above one it is undergo the compression, while the lower one it is undergo tension. It means the above we have the strain of the concrete and the lower we have the strain for the steel from the neutral axis here. But once your section has got a depth of D like this one, it means if you take the from the center of your bar above and the top of your section, you have create a certain distance, say D dash. So the distance from above to the neutral axis, it is assumed as x. Also the width it is carried as b, and below we have the area for the reinforcement or AS, and the above we have the area of AS dash. So the strain relationship is like this one. As we said, this is like a triangular. So once we have the equivalent, if we take the equivalent, we have the so-called stress block. The stress block, it is equivalent to the triangular strain, So if the distance from the neutral axis it is x, but once we assume it is equivalent to the, it is not a triangular, now it is a rectangular. So we have the block as a rectangular block. It means we take the equivalent of the mini triangular to a rectangular. So the equivalent, it is empirically the distance from above now, it is called S to the end of the block here. Now here there is a displacement, small tolerance. Now the value of S, this S, in relation to X, remember that the X is from the top of the neutral axis, this one. But now it is reduced. So the value reduced in relation S to X, it is considered empirically X is about 0.80% of the X, this one. So it means it is reduced, or it is less 20% from the previous value for X, in which the value of X is from above to the neutral axis, while the value of S, it is reduced by 20%. So we have the so-called stress block, and this was the strain relationship. It means the stress-strain relationship. So now, on consideration that one, now what is the so-called the concrete strength? Now the concrete strength, edge. The concrete increase its strength with respect to the edge. Now the increment rate decrease also with edge. We assume that the mature of the concrete is about 28 days. So by Eurocode 2, do not permit the use of the strength above or 28 days in calculation. So we assume the concrete strength should be in the age of 28 days, and it appear it is assumed strength. So once if it is 30, grade 30, it means after 28 we assume that the strength will meet the assumed strength of the concrete. So now the assumption or the empirically, we say after 3 days it is 1/3. After 7 days the strength should be at least 2/3, and after 28 days the full strength to appear. So that is the way the concrete strength we take or we assume to be after casting. Now we come back to the stress strain relationship as we said above. So the stress strain relationship, the stress, it is a function of F over A. Now the unit is Newton per millimeter. Now linearly, the strain, it is elongation. This is the strain, it is the elongation. So the strain, it is the elongation, change in the error over original length. Now linearly, elastic, and the full displacement. Now what happened? The strain, it is going straight to a certain edge. The relationship with the stress of the strain versus strain, it is linear to a certain edge or to a certain load. Now once you start to load, the stress strain, it is linear, and if it is linear, it is elastic one. But as it goes, it is going now it is going to have a certain nature. Now it is like a parabolic. Now as it goes, it is coming to a point where it is coming to it is deforming. Now we say that for non-linear plastic incomplete recover, and this is the point where you can go to the deformation. At any point the load, once you increase your load, the strain will come to break, and this is it deform. Now it is going to the permanent deformation. Once it is much loaded. Now the linear, the relationship now, once the concrete is going to permanent deformation, empirically we assume that the stress, it is reaching about this value, and this is the ultimate strain, in which the member, once it is loaded, it will become permanent deformation. It won't return back to its original as elastic limit. That's why once the member, or it is permanently loaded, it means the strain, it reaches to its ultimate. The value empirically from the empirical, it is estimated, or it is equivalent to 0.0035, and this is the assumption for the ultimate strain, in which the material, the member, once it is loaded, it is stressed, it is become permanent deformation. It won't go back to a linear as if to the original dimension. And that's why we say that the stress-strain relationship, it is the so-called parabolic response. Now, under that circumstance, we say that the stress-strain relationship of the concrete, it is in these natures. Now, we say that once the nature, as we said, it is sometimes linear, and then it is become parabolic. It means once it is loaded. So the value is this one, this value here. The value for the stress or the strain is this one. But this is the so-called design stress. But the design stress is lower than the characteristic strength of the stress-strain relationship. It means, because this is parabolic in nature, they said that the design stress is lower than the characteristic strength. It means if the characteristic strength is FCK, the design strength is FCD. Now this is lower, it is reduced to a certain percent. Now the percent of the reduction is due to the so-called the partial safety factor. It means we assume the structure of the member can suffer for the consequence for the something which is unforeseen. So we must to have a so-called a factor of safety in order to take for any contingency for the structure of the member. So that's why we say the relationship is bilinear. Bilinear stress strain. This is by simplicity. So the simplicity, we assume it is linear, while in normal it is parabolic 1. That's why if we assume it is equivalent to linear, we have certain percent which is reduced from the characteristic strength of the member of the concrete to the design strength. The design strength is always lower than the characteristic strength. That's the point to note. So the point or the amount which is lowered is given. Let's proceed. Now we say that the stress-strain relationship of the concrete. We say the compressive stress has traditionally been measured and expressed in terms of. Now how to measure it? We measure it from 150 cube, 150 mm cube, which is under clashing. After 28 days, we have the characteristic strength or the compressive strength of the concrete. Also, we can measure it from the 150 diameter cylindrical, in which are about 1 feet long, or about 300 mm or 30 centimeter long of the cylindrical. Also, the cylindrical strength is estimated about 60% of the cubical strength. So the equivalent between the cubical and the cylindrical is about cylindrical is take about 60% to the cubical. Now all the design calculation in the Eurocode are based on the so-called characteristic cylindrical strength. So this is under clause this one you can follow for your own time. Also, the cubical strength may, however, be used as a compliance purpose, in which the characteristic strength of the cubical is as follows. And these are the, say in terms of blade 35 to 45, so it is in this nature. Now you can go to the clause 316, you can have there, we say that the following. FCK, it is referred to the characteristic cylindrical strength. Now the compressive design strength, which is represented by FCD, it is a function of a partial safety factor of the concrete times the characteristic strength over the surface of the partial safety factor of the concrete. and this is refer about clause 2.4.2.4, which give the partial safety factor of the concrete is estimated, or it is computed about 1.5, and it means the value for the partial safety factor here, it is this value here as per the clause this one. Now for the tensile strength, the design strength for the tensile, the same as you times the recommended coefficients of the long efficiency times the characteristic strength over the partial safety factor. So this value A alpha cc, it is estimated to 1, it is recommended, or it is varying between 0.8 to 1 for the national annex. And this is the general formula for the characteristic or design strength in terms of characteristic strength must be considered by lower partial safety factor of the material. It depends on the steel or the concrete. Now as per the clause, you can from table 2.1 for the Euro code, the value of the partial safety factor for the concrete at the transient, it is about 1.5, while for the accidental is about 1.2, while the steel as the at the partial transient is 1.15, while the accidental is about 1.0, the same as the pre-stressed and in another natures. This is the way how you can take your partial safety factor according to table 2.1 as for Euro code. Now the modulus of resistance of the concrete. The modulus of resistance of the concrete, once you take the relationship of the stress strain, once you take the relationship of the stress strain, now once you take the relationship for the strain versus stress, you can have, as we said, that previously it is started as linear. The starting point here, it is linear, but it goes, as we said, it is going to parabolic like this one. So it means on the linear point, you can have the gradient here. The gradient is at about 40% of the mean strength or characteristic strength. So 0.4 times Fk, but the mean value of the compressive strength, it is above here. So the tangent here, the gradient, is the ratio between the stress versus the strain. So here you can have your strain at peak, and here you have the ultimate compressive strength. Means the strain now, it is the ultimate, in which the member it undergo the deformation. So now this one you can have from this clause table number 3, 1 as per Euro code. So the relationship between the stress strain, you can define the so-called E. So the tangent, it means the ratio between the stress versus strain. You have the so-called modulus of elasticity, and this by table 3.1 you can have its value. Now if you consider this table, you can have the modulus of resistance for the concrete. Now the value for the E, or the modulus of resistance of the concrete, as per the table, it depends on the function of the grade strength. if it is assumed a grade 20 to 25, the value of E, it is about this one. So the value it is respective to the grade strength. So you can pass it through on that table, and you can have the value whatever you need, the estimated value. So always we say that the modification factor is about 0.9, and this one 1.2 if you want to modify the values which you got. Now also, as we have the two relationship, as we said that the strain stress relationship. Now the first one, this one is for the hot load, and this is for the cold load, and this is the high yield elastic E for the hot cold working steel. Also you can have this nature for the hot load. It means here has got a kink before undergo the parabolic, while here it is going linearly and they go straight to parabolic. This is the vice versa, a curve between the hot load and the cold load, and this is the stress strain relationship for the steel as once it is loaded, and it depends on the nature whether it is hot load or it is cold load. The curve is difference. Here it goes linear and it is started to lower before it is going to parabolic, while here it is going linear, changing abruptly to parabolic. And this you can get from the graph from this figure as per Euro code. Now also the stress-strain relationship for the steel, we say that the inclination on the top of the strain, it is about EUD, and the maximum stress is K Fyk over the partial safety factor at certain value. So a horizontal top branch without a need, it is limited to this graph, and this graph give the linear relationship. So the value of K, it is a function of this one, while the mean, the design one, and this is the characteristic strength, as we said, should be lower on to allow the partial safety factor of the design. So this is the relationship between the strain and the stress for the steel. So the graph, it is this one, and this is per Euro code curve table or figure number, that one, where Ft is tensile stress and Fy, it is yielding stress. Now the value for the maximum stress, it is in this function. Now the durability. Durability of the concrete is influenced by now the cement type, the exposure of the conditions, now the concrete quality, now the cover of the river, and here also it is under these conditions, whether the soil it is underwater or whatever. You shall see this condition is very important. Also the humidity of the nature. Also if you take for the impervious, whether it is a chemical or aggregate, it is denser or whatever. So all these are the factors for the durability of the concrete. You may pass it through and look how it is affected to each other, and this factor is very important for the durability of the concrete. Email us with Kirumbi Engineering Skills at gmail.com, website Kirumbi Engineering Academy at ac.tz.